Hello friends, my name is IBM. I come yet with another episode of Learning Physics with me, and today I would like to take you through the concepts of alternating current. This is a short unit and I think it will be in only one episode. It will only be one part of solving past paper questions. Note that alternating current, electromagnetic fields, or electromagnetic induction and capacitors, there will be no clear boundary between these units. There will be some overlapping. There will be some overlapping between these units. So in alternating current, we shall need the concepts from electromagnetic induction, especially when we talk about transformers. Transformers use the concepts of electromagnetic induction, and therefore you should not be surprised when you find questions of electromagnetic induction in this part of alternating current. At some point, questions regarding capacitance, which we shall be recording in our next episode of learning physics, will also appear in alternating current. Therefore, don't expect a clear boundary between alternating current, capacitance, and electromagnetic induction. Once in a while, there will be some questions which cut across. So without wasting time, let's start with the past paper questions, and to be specific, let's move to our document. So you must have downloaded this document from the link attached on the video, and you must have printed it. To have it in hard copy is better, so you can always follow through the videos as you try to work out on hard copy. You can't watch and understand and learn from the videos by just watching the solved past paper questions without trying to work out on the hard copy document. To gain more confidence, have the copy or have the document in hard copy for easier practice. Okay, let us start with alternating current. In your document, just move to page 263, page 263, so that we can now start. So the first equation, we have a transformer. We have a transformer as shown in this diagram. The first question is saying explain why the core is made of iron. Why is the core of a transformer made out of iron? What do we know about iron? First of all, we know that iron is normally called soft iron because it can easily be magnetized and demagnetized. And what is the purpose of iron? Iron, because it can easily be magnetized and demagnetized, iron is also a good conductor. It can also help to increase the magnetic flux linkage with the secondary coil from the primary. And this therefore reduces the loss in flux. And of course, the end result will be minimizing energy loss due to magnetic flux leakage. So there are two terms I'm talking about here. There is linkage and there is leakage. So the purpose of iron is to increase magnetic flux linkage, to increase flux linkage, or to reduce flux leakage. Now I can say increase flux linkage or reduce flux leakage. So to increase flux linkage with the secondary coil, to increase flux linkage with the secondary coil, or to reduce flux loss. To reduce flux loss, or call this one now leakage. So iron concentrates the magnetic flux linkage. It concentrates. So instead of saying it to increase, you can say to concentrate. To concentrate the flux linkage with the secondary coil, that is the purpose of the iron. to concentrate flux linkage with the secondary coil, or to reduce flux loss, or to reduce flux leakage. That is the purpose of the soft iron. Okay. Next, explain why an EMF is not induced at the output when a constant direct voltage is at the input. Why do we expect that when there is a constant PD at the input, there will be no output? There will be no output EMF. I think that is very easy. We now borrow concepts of electromagnetic induction. We know that an EMF is only induced when flux in the core is changing according to Faraday's law, because the EMF induced is directly proportional to the rate of change of magnetic flux linkage. If the flux is not changing, then there will be no EMF induced. So we can say EMF is only induced. EMF is only induced, or is induced only. Let me change the English. EMF is induced only when flux in the core, or in the coil is changing. EMF is induced only when flux in the core or the coil is changing, and a constant direct voltage gives a constant flux. A constant direct voltage gives a constant flux. Or it gives a constant field. A constant direct voltage will give a constant flux or a constant field, therefore there will be no change in EMF. So that's why we don't expect an EMF to be induced when we use direct voltage or direct current at the input. There will be no EMF induced in that case, because an EMF will only be induced whenever there is a change in flux according to Faraday's law. And if there is no change in flux, then there is no EMF induced. If the flux remains constant, there is no EMF induced. Yet we know that a direct voltage gives a constant flux or a constant field. Part B, an alternating voltage of peak value 150 volts is applied across the 1,200 turns of the primary coil. The variation with the time t of the EMF E induced across the secondary is shown in the figure here. So you can see the figure using our concepts of SC, alternating current. We can first of all see the peak. It is alternating. The scale here is going to be 20 divided by 5, 20 divided by 5 small squares, so the scale is 4. So this is going to be 44, 48, 52. I think this is 52. Okay, so the peak value of the EMF is going to be 52. The peak is going to be 52. So note that EMF can also be considered to be voltage. So we can say, we know that V root mean square is equal to V naught over root 2. We have that at the back of our minds. If we want, we can just replace V with E for uniformity. They have given us the peak value of alternating voltage is applied, 150 volts is applied across the primary. So peak, they have given us peak values. Calculate the number of turns of the secondary coil. Calculate the number of turns of the secondary coil. We can still use peak values, there is no problem. Since we have seen that the peak value of EMF, I will call it E naught, is 52 volts. I will simply use the peak value because they've also given us peak value of the primary. This is the peak value of the secondary because it is the output voltage. So the peak value of the secondary, I'll call it E naught S for secondary. Let it be 52 volts. They have given us the peak value for the primary as 150. So E naught primary is 150 volts. So we look at the ratio of the number of turns in the secondary over number of turns on the primary is directly proportional to the voltage or the EMF of the secondary divided by the EMF of the primary. So we simply substitute to find the number of turns. They have given us number of turns of the primary to be 1200. 1200. So we now simply substitute. And when you substitute, you are going to see that the number of turns in the secondary is going to be equal to peak value of the second, which is 52, that is the output, over peak of the input is 150. You should be uniform when you're dealing with the peaks. Use the peaks. If you are dealing with the root mean square values, use root mean square values. Then times number of turns of the primary. This is 1200. So I press my calculator. 52 divided by 150 times 1200. So this is giving me 416. The number of turns is 416. State one time when the magnetic flux linking the secondary coil is maximum. Magnetic flux linking the secondary coil is maximum. Of course, when the magnetic flux linking the coil is maximum, the change is zero. The rate of change is going to be zero. And when the rate of change is zero, there is no EMF induced by Faraday's law. So we look for points where the EMF is zero. When the EMF is zero, it means the flux linkage is maximum and it is not changing. When the EMF is zero, the flux linkage is maximum and not changing. So on the graph, EMF is zero at t equals to zero. EMF is zero at this point here, which is I think 7.5. This is 7.5. EMF is zero at 150. At 15 milliseconds. So we have three values. EMF is also zero at this point here, which is 22.5. 22.5. So all those values, flux linkage must be zero. So E must be zero when flux is maximum or when flux linkage is maximum, according to Faraday's law and Lenz's law. The EMF is zero when the flux linkage is maximum because the rate of change will be zero. So you had to choose values from, for example, t equals to 0 milliseconds, t equals to 7.5 as we have seen from the graph, or t equals to 15.0 as we have seen from the graph, or t equals 22.5. Any of those times where EMF is zero, the flux linkage is maximum. So they want only one value of time, not several. So I have just given you all, you choose just one. A resistor is connected between the output terminals of the secondary coil. The mean power dissipated in the resistor is 1.2 watts. So average power is 1.2 watts. It may be assumed that the varying voltage across the resistor is equal to the varying EMF E shown in the figure 9.2. The varying voltage across the resistor is equal to the varying EMF shown in the diagram that we have seen above in the graph. So calculate the resistance of the resistor. So mean power, I would prefer to write this for average power. You must have seen from the lessons that you have had that average power is equal to V naught squared over R over 2R. You divide the V naught squared over R divide by 2. Or this can also be, average power can also be given as, now you can use the root mean square values. That is V root mean square squared divided by R. You just modify the equation for PD, I mean for power in direct values, that is V squared over R, that is power for direct values. Remember, alternating values have those values which have the same. The root mean square values are the values which have the same eating effect as the DC values. So instead of writing just V over R for DC values, we add V root mean square. So we now substitute. We can now substitute. The mean power is given as 1.2. The peak value of voltage we have seen from the graph was 52 divided by 2 times R, divided by 2R. Alternatively, we can say 1.2 equals to the root mean square value. We can find the root mean square value. Note that V root mean square, I will write it here. V root mean square is the same as V naught over root of 2. So this is going to be V naught, which is 52, divided by root of 2. That is the root mean square value of voltage. So this can be 52 divided by root of 2. This is squared divided by R. So in all cases, I'm going to make R. So I have two alternatives here that I'm giving at the same time. Okay, so for the first case, when you make R the subject here, R is going to be 52 divided by 2 times 1.2. So 52, it is actually 52 squared, not just 52. 52 squared. So 52 squared divided by, open brackets, 1.2 times 2. And this is giving me 126.67, which is to two significant figures is 1100 to two significant figures. You can also check this one here and see if it gives you almost the same thing. So 52 divided by root of 2 and then square, then divide by 1.2. It gives you the same thing. So this is when I make R the subject in this part, second formula, still R is going to be 52. Of course, 52 over root 2 is 36.8 squared. So this is 36.8 squared divided by 1.2. It gives you the same thing. So that is the resistance. Then on the figure 9.3, on the figure 9.3, sketch the variation with time t of the power P dissipated in the resistor. Remember, the power is always positive because I and V, power is I times V. Power is I times V, and I and V are always in phase for alternating current. When I is positive, V is positive, so the power is positive. When I is negative, V is negative, still the product is positive. So the graph is always above the x-axis. Good enough, they have only given us a positive, a grid above the x-axis. So they have given, and we have got that the average power is 1.2. The average power is 1.2. And if you remember, the peak value of power was given by I naught times V naught, and the average value of power was equal to I naught V naught over 2. That means the peak value of power can be got from multiplying the average by 2. So the maximum power here is going to be twice of 1.2. So P maximum is going to be 1.2 times 2, which is 2.4. So on my graph, my line should not go beyond 2.4. So from this grid here, the scale is 1 divided by 5, that is 0.2. So this is 2.2, 2.4 is here. My graph should not go beyond. My graph shall not go beyond 2.4. My graph shall not go beyond that line. Okay, so I need to look for the frequency. I need to look for the frequency from the graph, because I will not just sketch randomly. So I'm seeing that from this graph, this is in the middle here, it becomes the V becomes maximum at 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6.5. 6.5. V is maximum. Of course, when V is maximum, the power is also going to be maximum. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6.5. So somewhere here, I'll draw the peak. Then it becomes 0. It becomes 0 after another 6.5, I guess. So I'm starting from the center. Actually, it is 7.5. 1, 2, 3, 4, 5, 6, 7.5. It is 7.5. That's when it is maximum, not 6.5. So I have to change this. So 1, 2, 3, 4, 5, 6, 7.5. So after every 7.5, again it will become 0 after 7.5, I guess. So I'll have 1, this is a half, 1, 2, 3, 4, 5, 6, 7. So it will become 0 around here. Again, it becomes maximum after another 7.5. 1, 2, 3, 4, 5, 6, 7.5. So it is maximum here. A half, 1, 2, 3, 4, 5, 6, 7. It becomes 0 here. 1, 2, 3, 4, 5, 6, 7.5. It becomes maximum. Then a half, 1, 2, 3, 4, 5, 6, 7. Here it goes back to 0. That is at 22.5. Okay, so this is going to be a sinusoidal curve which never goes below the x-axis. It never goes below the x-axis. So you can draw a better graph, better than mine. Mine is just a simple sketch. It is hard to sketch on a computer, but at least I'm trying. So you must draw a very smooth curve, very smooth sine curve. You can make it bold. The peaks, where the peaks are, is what I started with. So your graph should depict that. The peaks should be at the right positions. The peaks are supposed to be at the right positions, corresponding with the time on the first graph that we saw, on the graph of E. Yes, I've tried to draw a better graph. What is very important are the positions for the peaks and where it goes back to 0. That is the most important. That is the most important thing here. The peaks and where it goes back to zero. So that will be the graph of power against time. That's not the maximum power. The average power was 1.2 and maximum power is twice the average power. Okay. The mean value of alternating current is 0. Explain why heating occurs when there is an alternating current in the resistor. Yes, we know that for alternating current, the mean value of current is 0. But still there is power dissipated when there is alternating current. The question is, why is there a power dissipated when we have alternating current going through the resistor? The reasons are very simple. First of all, we said voltage and current are always in phase, and power is going to be the product of V and I, which is always positive. So power is the product. Power depends on the product. Power depends on the product of I and V. And we know that I and V are always in phase. They are always in phase. So their product is always positive. So because their product is always positive, I times V is always positive, there is no point in time where the average becomes 0. Okay. Alternatively, you can think about the heating effect. You know that the heating effect is equal, depends on I squared times R. So the heating effect depends on the current squared, and I squared is always positive. The heating effect depends on current squared, and the current squared is always positive. I squared is always positive. That's why the heating effect, that's why there is power. There is power dissipated in a resistor even when there is alternating current. Alternatively, you can think about the graph. You can think about the graph of power against time. And if you try to sketch the graph of power against time, we have seen that it's always above the x-axis. So we can say power is always positive. P is always positive. And if P is always positive, there is no way the average will be 0. So there is power in the resistor. Transmission of electrical energy is frequently achieved using alternating high voltages. Suggest why high voltages. We saw in class, or you must have seen with your teacher in class, that for the same power transmission, high voltage means lower current flowing in the cables. And lower current flowing in the cables means less power loss in the transmission cables. So we can say for the same power transmission, higher voltages, let me just say high voltage, means smaller current or lower current flowing. Lower current flowing, hence less power less power loss in the transmission cables. That's why we use high voltages, and suggests why the voltage is alternating. Why is it that for transmission of electrical energy we normally use alternating voltage? First of all, we know that alternating voltage can be easily stepped up and stepped down using transformers. So this one can easily be stepped up. So it can be easily stepped up or stepped down. But normally we need it for stepping up. So I'll just say it can easily be stepped up for transmission. Can easily be stepped up to high voltages. Which we have seen it is advantageous in part 1. Alternatively, we could also say transformers only work. Transformers only work with AC. Transformers only work with alternating voltage. Alternatively, we could say generators produce alternating voltage. Generators produce alternating voltages. Alternatively, we could say it is easier to rectify than to invert. It is easier to rectify than to invert. It is easier to rectify. To rectify, remember, is converting alternating current to direct current using diodes. It is easier to rectify than to invert. That is to change it to another form. Next, the circuit for a full wave rectifier using 4 ideal diodes is shown here. So this is a bridge rectifier connected in the form of a diamond pattern. Diamond pattern. A resistor R is connected across the output AB of the rectifier. On the figure, draw a circle around any diodes that conduct when terminal X of the input is positive with respect to terminal Y. So let's check. When this one is positive and this is negative, it means current is flowing like this. This diode cannot conduct, but this one will conduct because it is in the correct orientation. This one will not conduct because current will not take this route, so the current will flow in this direction. So the current continues, it enters the load through a back. Now it can't go back to high potential, so it must take lower potential. It can't take this route. It will continue this route and therefore will take this route to go back to negative potential. So this diode will also conduct. So they said draw a circle around. So I am drawing a circle around these 2 diodes. Those are the diodes which are going to conduct because they are in the correct way. When X is positive, you can check what happens when Y is positive and X is negative in the next half cycle. Then label the positive plus and the negative minus terminals of the output AB. So let's check what happens in the second half cycle. In the second half cycle, I'll use a different color to see whether the diodes conduct. In the second half cycle, Y becomes positive and X becomes negative. Current must change direction. So current will flow, reaching here, it can't take this route. It cannot take this route. but it can take this route. It can take this route. So it reaches here, it can't take this route. So it continues flowing, again entering from the bottom. The first case, it entered from the bottom. The second case is again entering from the bottom, meaning that the bottom must be positive, the top must be negative. Therefore, they said label the positive and negative terminals of the output AB. So this is positive, the other one is negative because current is entering the load from the bottom. As simple as that. Then the variation with time t of the potential difference V across the input XY is given by the expression V is equal to 5.6 sine 380t. V is measured in volts and T is measured in seconds. Those are SI units. The variation with time t of the rectified potential difference across the resistor R is shown here. Use the expression for the input potential difference or otherwise to determine the root mean. When they say or otherwise, it means you can use any different approach or something that you think is necessary. To determine the root mean square potential difference, V root mean square of the input. So we know from our last lessons, V root mean square is supposed to be equal to V naught over root of 2. And from what they have given us, this is V naught, 5.6. So we shall say that V root mean square is 5.6 divided by the square root of 2. And when you press your calculator, I think this is obviously 4. So this is 4.0 as the root mean square value. Then the number of times per second, I think that is frequency, number of times per second that the rectified potential difference at the output reaches the peak. That is the frequency. Number of times per second that the rectified potential difference reaches a peak value. That is frequency. And we know that omega is equal to 2 pi times frequency. And omega from the equation, omega is this one. We are comparing with the general equation V is equal to V naught sine omega t. So omega is 380. So this means 380 is equal to 2 pi times f. So we find f is going to be 380 divided by 2 pi. I press my calculator. So from my calculator, I'm getting this one as I'm getting the frequency here as 60. The frequency here is 60.5. That is the frequency, but that does not answer this question. They say the number of times per second that the rectified potential difference at the output reaches a peak value. So note that in every one cycle, the rectified voltage reaches a peak twice. This one and this one, this is one cycle, but it is reaching the peak twice. Therefore, the number of times required here must be 12 times 60.5. So the number of times is going to be twice the frequency, because in every one cycle, the rectified potential reaches the peak twice in every one cycle. And frequency is just the number of cycles. So this will be 60.5 times 2, which will be 121 or 120 for that matter. It can be 121. Let me check. 380 again divided by 2 pi times 2. So it is 121 or 120. I think the best value would be 120 because the other one is less than. So two significant figures, it is approximately 120, even though here you get 121. Okay. A capacitor is now connected between the terminals AB of the output. The capacitor reduces the variation, that is the ripple, in the output to 1.6. So the ripple is reducing to 1.6. So we know a capacitor causes smoothing, prevents fluctuation or reduces fluctuation or variation to zero. It reduces the voltage, the output, from going to zero. On the figure sketch, the variation with the time t of the smoothed output voltage for time t equals t1 to time t equals to t2. Smoothed output voltage. Okay, so we want, they said the capacitor reduces the output, it reduces the variation to the in the output to 1.6. So the variation must reduce by 1.6. So from 6 minus 1.6, 6 minus 1.6, this becomes, instead of the variation being 6, the capacitor is reducing it to 1.6. So we say 6 minus 1.6. That is going to be 4.4. So our voltage will only fall to 4.4. The scale here is, I think, 0.2. So 4.4, these are two small squares. So our voltage should not go below this value here when it is smoothed. It's not to go along beyond this line here when it is smoothed. So we just draw now our straight lines. Of course, let's say we start with the charging part, this part here. But then when it is fully charged, when the capacitor is fully charged, then the voltage does not go below 4.4. So we shall draw peaks falling to 4.4. Here you use a straight line from the top, from the peak. You just use some kind of okay. Although they wanted up to T2, they wanted up to T2 between T1 and T2. So I can, okay, since they wanted between T1 and T2, this part is not necessary. I'll also remove that part and I concentrate on T1 and T2. So I have to consider parts of charging, so I have to draw this part here for charging of the capacitor. So it will look like that. You draw a very nice diagram, which of course this line has issues. It is going inwards. Have to make sure it is not entering in. Okay. So with a pencil and a ruler, you can draw something very neat, extremely neat, as shown there. The voltage does not fall below 4.4. It doesn't fall below 4.4. So they told us between T1 and T2, and that is as simple as that. So those are free 4 marks, extremely free. The peak values must not change, but all minimum values should be at 4 point, not 4.4. Did I say 6? Oh, sorry. This is not 4.4. It is 5.6 minus 4.4. I mean 1.6. It is 4.0. Sorry about this. This is not true. These videos are natural, so I must make mistakes. Therefore, when I'm drawing a graph, you must be using a pencil to check when there is an error, because I will not again erase the video to start afresh when there is an error, not at all. I want them to be as natural as they can. So the peak is 5.6, not 6. I don't know what is happening to me. So the graph should not go beyond or below 4.0. So the graph should not go below, the peak should not fall below 4.0, because, but it's the same process, so it was just an error. So starting from T1 up to T2, so this part is charging, this part is charging, this part is charging, the capacitor is charging, and then the discharging part starts from T1 as required. I'm using a ruler, so you can also use a ruler to draw something very neat. Okay, so that is the rectified voltage. That is the rectified voltage. Sorry about that. I had not seen very clearly. Okay. Suggest and explain the effect, if any, on the mean power dissipated in a resistor R when the capacitor is connected between terminals AB. What happens when we connect a capacitor? Suggest and explain the effect, if any, on the mean power, the average power. We are seeing that the voltage is now not going back to zero. What does that mean? It means instead of the voltage going to zero, it is stopping at a certain value. This increases the average power available. It increases the average power available. So what does this imply? So it means there is a high the amount of power available is higher, so the average or the mean power is going to be increased. So we can say the mean PD is higher now, the average PD is higher because the PD is not going back to zero. The average PD is going to be higher, which means the mean power is going to be increased. So we are going to say the mean value of PD, or the mean potential difference, is higher. This could be actually the root mean square. PD is higher, so you can also say the root mean square value of PD is higher. The root mean square value of PD is higher, and that means the power increases. This means the power increases. The mean PD is higher, or the root mean square PD is higher. Why is it higher anyway? It's because the capacitor supplies energy to the resistor. So the mean PD is higher since the capacitor supplies energy to the resistor. So the mean power is going to increase. So the mean power increases because the capacitor supplies energy to the resistor, which means the mean potential difference is higher. It doesn't go to zero. Therefore, the mean power increases. As simple as that. Okay? A simple transformer is illustrated here. Suggest why the transformer has an ion core. We have seen the purpose of the ion core. This one reduces loss of magnetic flux, or it increases magnetic flux linkage. So reduces loss of magnetic flux reduces loss of magnetic flux, or you can say it increases magnetic flux linkage. It increases magnetic flux linkage. That is the purpose of the iron core. It reduces flux leakage. That is the purpose of the soft iron core. Explain why the core is laminated. Why is the core laminated? We saw one of the sources of power loss in a transformer as being heating of the core due to eddy currents. And this was solved by laminating, that is putting insulating materials between thin strips of the iron what? I mean of the iron core. We saw that iron is made up of thin strips, that is a strip, and there is another strip overlapping, but between these two strips they put an insulating material. And I say that is what we meant by laminating. So laminating reduces the size of the eddy currents in the core, so the heating of the core is reduced. So this one reduces heating, reduces power loss due to heating of the core caused by eddy currents. It reduces power loss due to heating of the core caused by eddy currents. In other words, it reduces the size of eddy currents. It reduces the size of eddy currents. So laminating prevents eddy currents from building up to a larger value to cause a greater effect. That is laminating. Okay. By reference to the action of a transformer, explain why the input of the transformer is an alternating rather than a constant. We have seen a similar question like this. Why do we use alternating rather than direct? So we know that alternating current gives rise to a changing magnetic flux in the core, and the changing flux links the secondary coil. An EMF is induced in the secondary coil only when the flux is changing according to Faraday's law. So we are saying alternating voltage gives rise to a changing magnetic flux. To a changing magnetic flux in the core. The changing flux links the secondary coil. The changing flux links the secondary coil via the core, and EMF is only induced. An EMF is induced in the secondary coil only when flux is changing. When flux is changing, or it is when flux is cut. We know that a constant voltage produces a constant flux. This is just a by the way. A constant voltage produces a constant flux. So no EMF is induced. So that's why we use alternating, because alternating gives rise to a changing magnetic flux, which changing flux links the secondary coil, and by Faraday's law, an EMF is going to be induced. But if it is a constant voltage, it will produce a constant flux, and when there is a constant flux, there is no induced EMF. Okay, state Faraday's law. We stated Faraday's law many times in magnetic fields. The magnitude of the induced EMF in a coil the magnitude of the induced EMF in a coil is directly proportional to the rate of change of magnetic flux linkage. That is Faraday's law. The magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linkage. We stated that many times in magnetic fields and electromagnetic induction. An alternating current is passed through an air-cored solenoid. An ionic core is inserted into the solenoid and then held stationary within the solenoid. The current in the solenoid is now smaller. Explain why the root mean square value of the current in the solenoid is reduced as a result of inserting the core. There is an alternating current which is passed in the air core when there is no solenoid. Now we bring in an ionic core inside the solenoid, and we are seeing that the root mean square value now becomes smaller. It is reduced. First of all, bringing in the ionic core increases the magnetic flux because the ionic core concentrates the magnetic flux. So it means there is a change in magnetic flux, and an EMF is going to be induced in the ionic core. But then the EMF induced in the ionic core will also create a current in the ionic core, which will create its own magnetic field. And in accordance with Lenz's law, this will be opposing the EMF which is causing it. And therefore, it will be reducing the current in the coil. Therefore, we are saying that for the same current, the ionic core gives a larger flux linkage. In other words, it increases the magnetic flux, gives a larger flux linkage. Thus, larger rates of change in magnetic flux linkage. Thus, larger rates of change of flux linkage. So ion, remember, it increases the flux linkage. So the ionic core will give larger rates of change of flux linkage. That means there will be an EMF induced in the solenoid. So an EMF is induced in the solenoid. So the EMF induced in the solenoid, due to, of course, the current or the changing magnetic field in the core. So the EMF induced in the solenoid is greater for the same current. So the EMF induced in the solenoid is greater for the same the same current. The induced EMF, according to Lenz's law, the induced EMF, which is now induced in the solenoid by the core, the induced EMF opposes the applied EMF. By Lenz's law, the induced EMF in the solenoid opposes the applied EMF. So the current is smaller. Or we can say the induced EMF acts to reduce the current. So the logic here is very easy. Bringing a solenoid into a coil which is carrying alternating current. I mean bringing a core into a solenoid or a coil carrying alternating current. Bringing the coil increases the magnetic flux linkage. Remember, there is a changing magnetic field or a changing magnetic flux inside the core. The changing magnetic flux inside the core will also cause an induced EMF in the solenoid, in the solenoid or in the coil, which EMF induced in the coil again will act to oppose the change or the EMF which was applied to the coil. So that means it would reduce the current flowing in the coil. That is by Lenz's law. You bring the core, you get a large magnetic flux linkage. So it is changing. The changing magnetic flux in the core again will induce an EMF in the solenoid because the coils of the solenoid are cutting, or the coils of the solenoid are actually cutting the field created in the core. Therefore, an EMF which opposes the one applied to the solenoid is going to be induced again in the solenoid to oppose what is being applied. This reduces the current. That is in accordance to Faraday's law. Okay. Practical transformers are very efficient. However, there are some power losses. State two sources of power loss within a transformer. Number one, we mentioned hysteresis loss. Hysteresis loss. That is as a result loss due to changing magnetic field in the core, continuous magnetization and demagnetization. That is losses due to changing magnetic field in the core. We also saw heating of the core due to eddy currents. Heating of the core due to eddy currents. Heating of the core due to eddy currents. Note that eddy currents dissipate energy in form of heat. Number three, we talked about heating due to a current in the resistance of coils. Resistive heating of the coils. Resistive heating of the coils. That is the secondary and the primary coils. Since they have some resistance, there will be heating in the wires. We also talked about magnetic flux leakage. Magnetic flux leakage. Some magnetic field may leak to the surrounding, and that reduces the power output. So magnetic flux leakage, resistive heating, or heating due to the current in the resistance of the coils. Heating of the core due to eddy currents. Heating of the core due to eddy currents. Hysteresis loss. Hysteresis is HY. Hysteresis loss. hysteresis loss, that is loss due to continuous magnetization and demagnetization. Okay, next, the rectified output of a sinusoidal signal generator is connected across a resistor R of resistance 1.5K as shown in the diagram. The variation with the time t of the potential difference V across R is shown in the figure. This figure is faint, but we shall still use it. State how the rectification shown in the figure 4.2 may be achieved. When you look at this diagram 4.2, you notice that this is half wave. Half wave because half of the cycle is 0 and there is only voltage in another half of the cycle. So it is half wave rectification. And we achieve half wave rectification by inserting a single diode in a series with a load. So since they just want it in writing, connect a single diode in series with the R or with the resistance. So connect a single diode in a series with R or in series with the supply, in series with the AC supply. You will have half wave rectification. A capacitor is now connected in parallel with the resistor R. The resulting variation with time t of the potential difference V across R is shown in the figure. So now it is smoothed because they have connected a capacitor. Use the figure to determine the mean potential difference, that is the average potential difference. So the maximum is 6.0 from the graph, and the minimum, this is 6, it is falling to this point here, that is 1, 2, 3 small squares. The scale here is, there are 5 small squares, that is 2 divided by 5, which is 0.4. So it has fallen by 3 small squares, so it is 6 minus 1.2. So it is here. I think that is 4.8. So we shall say 6.0 plus 4.8 divided by 2 to get the average potential difference across R. And I think this is 5.4 volts. Then the mean current in the resistor, of course, V is equal to I times R. The mean current in the resistor, since we have the average value of V, this will be equal to the average value of I times R. So the average value of current is going to be the average of V, which is 5.4 divided by R. They told us it was 1.5 kilo ohms, that is R. So we shall just divide this by 1.5 times 10 power 3. And when I press my calculator, so this is 3.6 times 10 power negative 3. The time in each cycle during which the capacitor discharges through the resistor. Time. Let's look for time for discharge. We may not be sure about this part where it is 0, so we can start from 0.3. From the peak here, this part, remember, it is charging, then here it is discharging, and it is discharging up to here. So this is 0.03, and this is 1, 2, 3, 4, 5, 6, 7. Those are 7 small squares. On the x-axis, each small square is each small square we have 0.01 divided by 10. That is 0.001. Each small square is 0.001. So these are 7. So that is 0.007. So this must be 0.057. 0.057 here. So this is going to be 0.057 minus 0.037. 3, which gives us 0.027. So the time for discharge is between this point here and this point here, that is discharge. Or you could check 0 to this point here, that is 0.027. So the time is 0.027 seconds. Use your answer in Roman 1 to calculate the charge passing through the resistor during one discharge of the capacitor. Charge passing through the resistor. So charge is equal to I times T. Charge is I times T. We have seen the time of discharge and the mean current. So this will be average. So this will be 3.6 times 10 power negative 3 times 0.027. Press the calculator. So from my calculator, I am getting 9.72 times 10 power negative 5 coulombs. Then the capacitance of the capacitor. The capacitance of the capacitor, we have seen capacitance. So C is equal to so capacitance will now be the change in the charge over the difference in the value of V. So the charge passing through the resistor during discharge is 9.72 times 10 power negative 5. And the value of V, the change in V correspond to that discharge, is actually between this peak and this one, I think this is 1.2. That is 6.0 minus 4.8. So the difference in the potential is 6.0 minus 4.8, which is 1.2. So we divide this by 1.2. We shall divide this by 1.2. And when we divide by 1.2, this is giving me so this is giving me 8.1 times 10 power negative 5. A second capacitor is now connected in parallel with the resistor R and the first capacitor of the figure as shown, figure 4.3. Draw a line to show the variation with the time t of the potential difference V across the resistor. So when the second capacitor is connected in parallel with the first one, it means total capacitance increases. Because for capacitors in parallel, the total capacitance is equal to C1 plus C2 if they're in parallel. So total capacitance is higher. And remember in class, you must have said that when capacitance is higher, it means a higher capacitor discharges slowly. That means the PD, the smoothing is increased, so the fluctuation is reduced. So we want to draw a line on the graph. We want to draw a line on the graph showing the variation with time for the potential difference when we have now two capacitors in parallel. So I will draw a line with a reduced peak, a line which has a reduced peak, which has a reduced fluctuation. So I will draw it around here. Let me say now this is what is happening. So that is charging, that's discharging, and this will be here. Sorry, this is not very good. So that is what we shall have. There is more smoothing. In other words, the fluctuations reduce, the ripples reduce, as shown there. Okay. Next, the variation with time t of the current I in a resistor is shown in the figure, as you can see. the variation of the current the variation of the current with time is sinusoidal. Explain why, although the current is not in one direction, only power is converted in the resistor. You should be thinking about that. Look at the graph and think about why there's power in the resistor, to be precise. So we have answered a similar question. We have answered a similar question in the past. Okay, so this question is about what power depends on. Power is equal to I times R, or I squared times R. So if it is alternating, I and V are always in phase. The product is always positive, so there is power dissipated in the resistor. Alternatively, power is I squared R, and I is squared, which means the square is always a constant. I mean, the square is always positive, so the power is always positive. So we can say power or heating, the power or heating in the resistor depends on I squared. Depends on I squared. So it is independent of the direction of current. Independent on current direction. It is independent on the current direction because, or since, I squared is always positive. Alternatively, we could say power is I times V, and I times V is always positive since they are always in phase. Okay, so power depends on I squared, so it is independent of the current direction since I squared is always positive. I squared is always positive, as simple as that. Use the relation between root mean square current and peak current to deduce the value of the ratio average power converted in the resistor over mean power converted in the resistor. Average power converted in the resistor over maximum, not mean. Mean power converted in the resistor. They want us to use the root mean, the relation between root mean square current and peak current. So we know that maximum power is equal to I naught squared times R. That is maximum power. And we know that maximum peak value is equal to I root of 2 times the root mean square value of current, which means the maximum power maximum, can be the same as I root mean square squared times R. I just replaced this. I just replaced that. It will be I root mean square. It is I root mean square squared times R. Actually, this is times, this is going to be times 2. It is twice I root mean square squared times 2. That is the maximum power. It is I root mean square squared times 2 because of substituting for I naught squared. Then the average power, of course, the average power, as we have already known, the average power is simply I root mean square squared times R. So this means we just combine these two equations to find the ratio. So the ratio is going to be For max average, which is I root mean square squared times R, divided by for maximum, which is root of 2 times I root mean square squared, then times R. So when you simply substitute or simplify, R cancels, you remain with I. The ratio is I root mean square squared divided by twice I root mean square squared, which is a half. That is a half, and a half is 0.5. So you just play around with these expressions, just play around with them. Maximum power is I naught squared R, but I naught is root 2 over I root mean square. Then you substitute, you get that expression. And now our average power is just I root mean square squared times R, because the root mean square values correspond to the average values. They give the same effect as the average. The same heating effect as the DC values are the root mean square values. Okay, a simple ion cored transformer is illustrated here. This ion cored. Simple ion cored transformer is illustrated there. State why the primary and secondary coils are wound on a core made of iron. We know now what iron does. So this is to improve flux linkage, to increase flux linkage, to reduce flux loss. So this is to improve or to increase flux linkage, to increase flux linkage or to reduce flux losses. So that means it minimizes power loss. Okay. Suggest why thermal energy is generated in the core when the transformer is in use. Now that is Faraday's law. So the flux in the core is also changing, and the changing flux induces an EMF according to Faraday's law. The EMF in the core also produces different currents, which we call eddy currents, which cause the heating of the core. So we are saying the flux in the core is changing. Flux in the core is changing because of the alternating current in the primary coil, and then the changing flux induces eddy currents. In the core. The induced eddy currents dissipate energy in the core. So the induced eddy currents in the core cause heating. The induced eddy currents in the core are the ones responsible for heating. So that is Faraday's law is showing us that because there is a changing flux in the core, there's an EMF in the core which produces eddy currents. These eddy currents are the ones which dissipate energy in the core as heat. Okay. The root mean square voltage and the current in the primary coil are Vp and Ip respectively. The root mean square voltage and the current in the secondary coil are Vs and Is respectively. Explain by reference to direct current what is meant by the root mean square value of alternating current. So that value of direct current which produces the same power or heating effect in a resistor as alternating current is what we call the root mean square value. So the root mean square value is that value of alternating current, the value of alternating current producing producing the same power, the same mini power or heating effect in a resistor as direct current is the root mean square value of alternating current. The value of alternating current which produces the same mini power or heating effect, the same mini power or heating effect in a resistor as direct current is the root mean square value. Show that for an ideal transformer, Vs over Vp is equal to Ip over Is. So if the transformer is ideal, the power in the primary should be equal to the power in the secondary, and the power in the primary coil should be equal to the power in the secondary coil. And this means we know power is IV, so we shall say I primary times V primary is equal to I secondary times V in the secondary, which therefore implies that Vs over Vp is equal to Ip over Is. The marks are for stating this and that is all. Not proving backwards. A student is asked to design a circuit by which a direct voltage of peak 9.0 volts is obtained from 240 volts. A direct voltage of that peak value is obtained from 240 volts. The student uses a transformer that may be considered to be ideal, that is 100% efficient, and a bridge rectifier incorporating 4 ideal diodes. The partially completed circuit is shown here on the figure. Draws symbols for the 4 diodes so as to produce a polarity across the load as shown in the diagram. So we want up to be positive. So that this diode must therefore conduct. This diode must be conducting, and it will be parallel to this one. Just join here. Then, so if this diode conducts, this one should also be conducting. Then that will be a complete cycle. Then the next half cycle, this diode and this one should conduct to make sure that this is positive. So it means this should be in this direction. You can use a ruler to draw a better diagram, but I can still make mine better too. Okay, so from that diagram, you notice that at least there is evidence that you can use a ruler to draw very neat diagrams, better than mine. Very good diagrams, better than mine. Okay, so that is the diagram that we shall have. So when you look at this diagram, you are going to notice that actually the diodes are conducting in that particular direction, and therefore it means the upper part is going to be positive and the bottom part is going to be negative. Part B, calculate the ratio number of turns on the secondary coil over number of turns on the primary coil. Note that the value which is normally quoted here is not actually is actually the root mean square value. But the value which was quoted here was actually peak value. So you must use uniformity. When you choose to use peak values, use peak values. When you choose to use root mean square values, use root mean square values. Okay. So number of turns of the secondary over number of turns of the primary is going to be equal to V secondary over V primary. For the secondary, they have given us a peak value, yet for the primary, we have root mean square. So we shall use root mean square values. We shall use root mean square values to be uniform, or you can change to peak values, or we can even use peak values to be uniform. We know that the peak value is going to be root 2 times V root mean square. That is for the primary, since the secondary is given as peak. So the ratio we want is going to be V secondary. They have given us peak as 9.0 volts, and V primary, which they have given us root mean square, but we have changed to peak as root 2 times 240. We now press our calculator. 9 divided by root 2 times 240. And this is giving me a ratio which is 0.027. 0.027. So that is the ratio we are talking about here. Number 7. Explain what is meant by root mean square value of alternating voltage. Root mean square value of alternating voltage. From the lessons, we know that this is the value of steady or constant voltage or direct voltage that is going to produce the same average power in a resistor as the alternating voltage. So the value of direct or constant or steady voltage that produces the same heating effect, the value of direct or steady voltage that produces the same power in a resistor, or the same average power to be specific, or the same mean power in a resistor as alternating voltage, or as the alternating voltage. That is what we call the root mean square value of alternating voltage. It is that value of alternating voltage, or direct voltage to be specific, that produces the same mean power or the same heating effect in a resistor as the alternating voltage. Normally, when I put here the article day, the meaning comes out very fast, or very easily, or very clearly. Either you start by looking at the alternating, that value of the alternating voltage, which has the same mean power or causes the same mean power in a resistor as direct or steady voltage. It is root mean square value. Okay. So an alternating voltage V is represented by that value. For this alternating voltage, determine the peak. You just compare with the V equals to V naught sine omega t. So the peak is 220 without wasting time. Then the root mean square value, we know that V root mean square is equal to V naught over root 2. So this will be 220 divided by root of 2. And this gives us, pressing my calculator, 220 divided by root of 2. So this is 156. That's 156. Okay, next, the frequency. We know that frequency, they have given us omega as 120 pi, and we know that omega is equal to pi times f. So we shall say 120 pi is equal to pi f, and when you press your calculator, you see that omega is 60. I mean frequency f is 60, 120 pi divided by 2 pi, that is 60. And in part C, the alternating voltage in B is applied across a resistor such that the mean power output of the resistor is 1.5. So we want the output, the average power to be 1.5 times 10 power 3 watts. But remember, average power is equal to the root mean square value. Because we are dealing with the average power is related to the root mean square value. So this is V root mean square squared over R. Instead of using V over R, because it is average for alternating, it is V root mean square. So this will be V root mean square squared divided by R. So we want to find R. So this means 1.5 times 10 power 3 is going to be V root mean square, which I have got above as 156. So this is 156 squared divided by R. So when I cross multiply and I find R, I'm seeing that R will be 156 squared divided by 156 squared divided by 1.5 exponent 3. And I am getting 16. I'm getting 16. Alternatively, you could choose another expression depending on what you have, but this is the most direct one because we have voltage, so we shall use root mean square value of V. Okay. Next, a bridge rectifier contains 4 diodes A, B, C, and D as shown here. The output of the transformer is rectified is connected to load L of resistance 2.4 as shown. On the figure, mark with the letter P the positive terminal of the load. So let's move around the circuit. When this terminal is positive and this is negative, current is flowing like this. This cannot conduct, this cannot conduct. That means, sorry, this cannot conduct, this one conducts. So current is taking this route. It can't take this route, so it will take the downer route and enter from the bottom. Continue, it will have to take the other side, taking this side and back to, it can't take this side of B because it will be going back to high potential. So to go through C and back to A. So in the first half cycle, it is A and C which are conducting. In the second half cycle, this is the first half cycle. In the second half cycle, this becomes positive, the other one becomes negative. So current is now flowing this direction. C cannot conduct, D conducts. So when D conducts, it can't take that route. It enters from the bottom. Then again, when it enters from the bottom, again B conducts. So it is D and B conducting in the second half cycle. So in all cases, it's entering from the bottom. So we are going to mark a point at the bottom and label it P as required. So positive is down, negative should be up. The variation with the time t of the potential V across the input to the rectifier is shown here, as you can see. That is the variation. You see that the peak is 6. The maximum is 6. That is the peak voltage. Calculate the root mean square current. Calculate the root mean square current. So we know that V root mean square is, because they have given us V root mean square is V naught over root 2. And we also know that from Ohm's law, we know that V is supposed to be equal to I times R. Because we are dealing with the alternating, this will be V root mean square will be equal to I root mean square times R. So we now substitute. We can now substitute. So this is going to be V root mean square is going to be V naught over root of 2. which will be equal to I root mean square times R. We now put in the quantities. From the graph, V naught is 6. So we shall have 6 divided by root of 2 equals to I root mean square times R. And they gave us R from the question as 2.4 kilo ohms. So this will be 2.4 times 10 power 3. So we just simply divide 6, divide by root of 2, then divide by 2.4 exponent 3. And this is giving me a 1.77 times 10 power negative 3, or approximately 1.8 times 10 power negative 3 amperes. The potential across the load L is to be smoothed using a capacitor. On the figure, draw the symbol for a capacitor connected to produce smoothing. So the capacitor must be connected across the load. Therefore, we shall draw our capacitor here. So that is the capacitor. Okay, that is a free mark. It is connected across. The minimum potential difference across the load L with the smoothing capacitor is connected is 3. So it means the PD should not go beyond 3 volts. Sketch the variation with time t of the potential difference across the load. So the PD should not go below 3. So the minimum is 3. So 3 I think is in the center here. 3 is in the center here. 3 is in this. I'm just using a dotted line. It is not necessary. You can just put mark points. So we need to draw a graph according to the question. Sketch the variation with time t of the potential difference across the load. When there is a capacitor, the PD is only going to fall to 3. It will not go below 3. So I'm going to just draw the discharging part of the capacitor. I will use almost straight line. So a line coming from the peak it should be in the center because I think that's where 3 is. From the peak to that center. Then the charging part of a capacitor should also be sketched. Just pass your pencil there. Something like that. Okay, so that is the smooth part. Those 3 marks are always free marks. So when you practice this, they become part of you. They are always free marks. That is for the smoothed part. Okay, next, the variation with time t of a sinusoidal current I in a resistor is shown in the diagram. The resistance is 450 ohms. Use data from the figure to determine for the time t equals to 0 to time t equals to 30, the frequency. So we can first see the period. The frequency is equal to 1 over the period, and this is 1 over. And the period is, I can't count period from here up to here, but I can consider this point here and that point there. And you notice between 10 and 25, the period should be 15. So this is going to be 15 times 10 power negative 3. So that is the period. Pressing the calculator to get the frequency. So the frequency is approximately 67 to 2 significant figures. Then the mean current, this is alternating. The average value of current for alternating current is 0. So here the answer is 0. Then the root mean square value of current, I root mean square is equal to I naught, that is the peak, over root of 2. We substitute the peak value of current, you can see it from the graph. I think this is 0.75. This is 0.75. It is in the middle of 1 and 0.5. So this is 0.75. So this will be 0.75 divided by root of 2. Then I press my calculator. So this is 0.53 amperes. 0.53 amperes. Then the energy dissipated by the resistor. Energy dissipated. So we know that power is equal to energy over time. So it implies that energy is going to be power times time, and this will be the average power. So this is going to be the average power times time, which is going to be I root mean squared times R, that is the power, average power, then times T. Remember, when we are dealing with average power, you consider root mean square values. In the equation, power is equal to I squared R. For average power, we take the average value, the root mean square value of I is the one which produces the average power. So when we substitute, I root mean square is 0.53 squared times R was given as from the value of R was given as, I think, 450. It is there. R is 450. Then the time is I think time is between 0 and 30 milliseconds, so the time is 30. So the time is 30 times 10 power negative 3 to change it to seconds. So I press my calculator. So from my calculator, this is 3.8 joules. 3.8 joules. Okay. The components of a bridge rectifier are shown in the figure below. As we can see, complete the circuit of the figure by showing the connections of the supply and of the load to the diodes. So we want there to be an output which is full wave rectified from this side. So I think this, let me try to connect this here. When I connect that here, if this is positive, this diode will conduct. This will not. That means I will need a link directed to the load there. So this conducts, this does not. So current takes this route into the load. It must come here. So when it comes here, it can't take this route. So I must link this point here to the other side. So I'll have as simple as that. So I can increase this thickness so that people can see what I'm doing here. So I have connected this one to this one. You can't draw this with a pen. You first draw with a pen, so as you move around you navigate around around your connection to see if there is a load, there's a complete path to the load. And you reverse the terminals to see if you enter the load or the current is entering the load from the same side. If not, then the connection is wrong, because this is full wave rectification. Suggest one advantage of the use of a bridge rectifier rather than a single diode. Remember, for a single diode, that was half wave. So we know that for a full wave, there is always power on every half of the cycle. So we say there is power supplied. There is power supplied on every half. On every half cycle. There is power supplied on every half cycle, giving a greater average power. Giving a greater average or mean power. As long as there is power in every half cycle, then the average power is going to be higher. But if you remember half-wave rectification, for the first half there is power, there is a voltage, the second half there is no voltage. It meant that the average power was reduced. Okay. State what is meant by smoothing. By putting a capacitor across the load, we saw that we achieved smaller fluctuations. The voltage would not go directly to zero. So smoothing is the reduction in the variation. Reduction in the variation of the output unidirectional current or voltage. That is what we call smoothing. Reduction in the variation of the output unidirectional current or voltage. We prevent the output to go to zero. That reduction in the variation is what we call smoothing. State the effect of the value of capacitance of the smoothing capacitor in relation to smoothing. Your teacher must have told you that capacitance, what determines the smoothing is the product RC, which we call the time constant. A larger capacitor discharges slowly, or it makes RC larger, so it means the smoothing increases. So we can say that for the same load, if we have not changed the load, for the same load, that is for the same resistor, a large capacitance, a larger capacitance means the product RC is larger, and this produces more smoothing. So if the load is the same and we increase the capacitance, for a larger capacitance, the product RC, which we call the time constant, is going to be larger, and this produces more smoothing or better smoothing. The variation with the time t of the output view of an alternating voltage supply of frequency that is shown in the figure below. So this is what we have. Use the figure to state time T1. So this is 1 cycle and a half. So T1 is a period plus a half a period. We can find the period. They told us the frequency is 50, so period is equal to 1 over 50, which is 0.02. So it means T1 is going to be 0.02 plus a half of 0.02, which gives us 0.03. So the time T1 is 0.03. That is 1 cycle and a half. The peak value of V0. Just look at the graph here, and I think that is 17. So this is 17.0. Then the root mean square voltage, V root mean square. We know that V root mean square is equal to V0 over root of 2. V0 is 17.0 over root of 2. V0 is 17.0 over root of 2, so we press the calculator, 17 divided by root 2. So this is 12.0. Then the average, I think the average is 0 because this is alternating voltage. The mean value of alternating voltage is 0. So that is 0. Then the alternating supply is connected in series with a resistor of resistance 2.4 ohms. Calculate the mean power displayed. When you are dealing with the mean power, talk about root mean square values. Just look at the formula for power as V over R, but then V should be root mean square. So the average power is going to be V root mean squared divided by R. And this is 12.0 squared divided by R, which is 2.4. When I press my calculator, this is giving me 60.2 watts. Okay. An alternating current supply is connected in series with the resistor R as shown here. The variation with the time t in seconds of the current I in amperes in the resistor is given by the expression I is equal to 9.9 sine. So you compare with I is equal to I naught sine omega t. For the current in the resistor R, determine the frequency. So you see omega is 380, and we know that omega is 2 pi f, which is 380. So frequency is going to be 380 divided by 2 pi. I press my calculator, 380 divided by 2 pi. That is 60.5. 60.5 hertz. So that is 60.5 hertz. Then the root mean square value of current, I root mean square is equal to I naught divided by root of 2. And from here, I naught is 9.9 divided by root of 2. I root mean square, and this is giving me 7.0. 9.9 divided by root of 2. 7.0. To prevent overheating, the mean power dissipated in the resistor R must not exceed 400 watts. The average power should be 400 watts, and average power is going to be I root mean squared times R. So 400 should be equal to I root mean square, which is 7.0 squared times R. So it means R is going to be 400 divided by 7.0 squared. I press my calculator, and this is 8.2 ohms. A transformer is illustrated in the figure 6.1. We have a laminated iron core, primary coil, secondary coil, and a load. We have alternating voltage supply there. Explain why the coils are wound on a core made of iron. So we saw what iron does to increase the magnetic flux, to reduce flux losses, to concentrate magnetic flux. So iron, that is to concentrate or to increase magnetic flux, or you can say to reduce flux losses. Or you can say to reduce flux losses. Suggest why thermal energy is generated in the core. We have answered this question, why there is thermal energy. There's a changing flux in the core which induces an EMF which produces eddy currents in the core. The eddy currents in the core give rise to the heating effect. So the changing flux in the core induces eddy currents. The changing flux in the core induces eddy currents in the core. The eddy currents in the core give rise to a heating effect. Give rise to a heating effect. The changing flux or magnetic flux in the core induces eddy currents in the core, and it is these eddy currents in the core that give rise to a heating effect in the core. So that's why there's thermal energy generated in the core. State Faraday's law of electromagnetic induction. Remember I said there will be always overlap of electromagnetic induction, AC, and capacitors or capacitance. So the magnitude of the induced EMF magnitude of the induced EMF in a coil is directly proportional to the rate of change of magnetic flux linkage. Magnetic flux linkage. Use Faraday's law to explain why the potential difference across the load and the EMF of the supply are not in phase. When we were explaining the principle of operation of a transformer, we noticed that actually the potential difference across the load, that is the secondary, was not in phase with that in the primary. That is just in accordance with Faraday's law. So the magnetic flux in the primary coil or in the core is always in phase and proportional to the current in the primary or the EMF in the primary. The magnetic flux in the core is in phase and proportional to the EMF or to the current in the primary coil. Yet an EMF is induced across the secondary. The EMF induced across the secondary is proportional to the rate of change. Yet, the magnetic flux in the core is in phase and proportional to the EMF in the primary coil. But the EMF induced in the secondary or induced across the secondary coil is proportional to the rate of change. Is proportional to the rate of change of flux. So if one is proportional to, the other one is proportional to the magnetic flux, and the other one is proportional to the rate of change, these two cannot be in phase because when the magnetic flux linkage is maximum, the rate of change is zero. And when the magnetic flux linkage is zero, the rate of change is maximum. So these cannot be in phase. So EMF supply is not in phase with the PD across the second. So the EMF of the supply cannot be in phase. Cannot be in phase with the PD across the secondary coil. When magnetic flux is maximum, the rate of change is zero. When the magnetic flux is zero, the rate of change is maximum. So magnetic flux is directly proportional to the EMF in the primary and is in phase. But the EMF induced in the secondary is directly proportional to the rate of change of the magnetic flux. So the two cannot be in phase. So the EMF of the supply cannot, I know some students just watch the videos without listening. So cannot be in phase with the PD across the secondary coil. Electrical energy is usually transmitted using alternating current, suggests why transmission is achieved using high voltages. High voltages. We have said for the same power transmission, if the same power is to be transmitted, then high voltage is better, because at high voltage, a low current or a small current flows. A small current flows. And a small current means less power dissipated in the transmission cable. So thus less power or less energy loss, or less power dissipated, less energy loss in the transmission cables. So this was the advantage as to why power is transmitted at high voltage. That is when we're using a step-up transformer. At high voltage, a small current flows, and if there's a small current flows, the power dissipated depends on I squared R. So a small current means a small power dissipated. Alternating current, suggests why the transmission is achieved using alternating current. Why alternating and not direct? So we know the advantages of alternating. It can easily and readily be stepped up. It can easily and efficiently be changed. So it can, so let me say alternating voltage can easily and efficiently be changed, of course, by transformers. Alternatively, you could just say transformers work with alternating voltage only. Transformers only work with alternating voltage. Transformers only work with alternating voltage. A sinusoidal alternating voltage supply is connected to a bridge rectifier as shown, or four ideal diodes. The output of the rectifier is connected to a resistor R and a capacitor C as shown here. You can have a look at the diagram. The function of C is to provide some smoothing to the potential difference across R. The variation with the time of the potential difference across the resistance R is shown in the figure. So let's look at the figure. Look at the figure here. So the negative parts have been removed. Use the figure 6.2, which is now the graph, to determine for the alternating supply the peak. The peak, you just look at the graph and you see it is 4. So the peak is 4.0 volts. The root mean square voltage, since we have the peak, we know that V root mean square is going to be equal to V root mean square is equal to V root mean square is equal to I naught over root 2. So I use the figure to determine the root mean square value. So it means since the peak value of voltage is that, then V root mean square value is going to be 4.0 divided by root of 2. 4.0 divided by root of 2. My calculator, 4.0. This is 2.82 or 2.8. 2.8283 or 2.8 volts. Then frequency, show your working frequency. So frequency is going to be 1 over T, and this will be 1 over, we look for the period. So period, I can start from here. This is half a cycle. This is a full cycle here. That is the period. Because remember, if you had alternating, this part here is charging, then discharging, that is half a cycle. Charging, discharging, that is another half a cycle. So the period will be either from here up to there, which is, this is 2, and this is 22, that is 20. So the period is going to be 20 milliseconds, 20 times 10 power negative 3 milliseconds, because it was milliseconds. So that is the period. When I press my calculator, this is giving me 50 hertz. Then the capacitor C has capacitance 5.0 microfarads. For a single discharge of the capacitor through the resistor R, use the figure to determine the change in potential difference. It starts from 4 and falls up to this value here is 2.4, because the scale here is 2 over 5, which is 0.4. So that is 2.4. From 4 to 2.4, so this will be 4 minus 2.4. The change is 1.6. So that is 1.6 volts. Determine the change in charge on each plate of the capacitor. So change in charge, we now use capacitance C plus change in V. So this will be 5.0 times 10 power negative 6. Change in V is 1.6. Pressing the calculator, 5 times 1.6, that is 8.0 times 10 power negative 6 coulombs. Show that the average current in the resistor is 1.1 times 10 power negative 3. Average current in the resistor. So the average current in the resistor will simply be equal to the change in the charge divided by change in the charge, because current is charge over time. So the change in the charge over the time for the discharge, change in the charge over the time for discharge, and from the graph, time discharge starts from here. Discharge starts from around here and stops to this point. So this is, I think this is, it starts from 1, 2, 3, 4, from 5 to 12. That is 12 minus 5. 12 minus 5, that is 7. So discharge time is 7 milliseconds. That's when the charge changes. So this will be the change in time, which is 7. So this is going to be 8.0 times 10 power negative 6 over the change in time, which is 7 times 10 power negative 3. So when you press your calculator, this gives you divide, that is 1.14 times 10 power negative 3 amperes, which is approximately equal to that. Use the figure 6.2 and the value of the current given in part B to estimate the resistance of the resistor. So we know that from the figure, the average value of PD is going to be 4 plus 2.4 divided by 2. That is the average. So the average value of PD, is going to be 4.0 plus 2.4 divided by 2. That is maximum plus minimum over 2. So the average value of PD is 3.2 volts. That's the average value of PD. And of course, we can now use our current I is equal to, V equals to I times R. V is equal to I times R. So I want to find R. So R is going to be the average value, which is 3.2, divided by the current 1.1 times 10 power negative 3. I press my calculator. So this is to two significant figures, 2,900 ohms. Okay, next. A simple transformer is illustrated here, as you see. A simple transformer is illustrated here, as you can see, state why the iron core is laminated. Laminating does not prevent eddy currents. It just reduces power loss in the core due to eddy currents. So it minimizes just the eddy currents from growing up. So to reduce energy loss or power loss in the core due to eddy currents. Okay, state what is meant by an ideal transformer. For an ideal transformer, there is no power loss. There is no power loss in the transformer. So it means the input power is equal to the output power. That is ideal. Practically not achievable. An ideal transformer has 300 turns on the primary, 100 turns on the secondary. The root mean square input voltage is 9 volts. This is the root mean square. Calculate the peak voltage across the load resistor connected to the secondary coils. They have given us peak, the root mean square, and they want the peak value of voltage across the secondary. So using a ratio of number of turns, you could say number of turns in the secondary over number of turns in the primary. Now you choose, since they have given us, they want peak, we can use peak values of voltage. So this will be voltage. Peak value of voltage in the secondary, I'll call it V naught S over peak value of voltage in the primary. I'll call it peak V naught P. So it means we want to find the peak value of voltage across the load in the secondary. So we are now substituting. Number of turns of the secondary is 8100. Number of turns of the primary is 300. Peak value of voltage in the secondary is what we want to find, V naught in the secondary. Peak value of voltage in the primary, they have given us a V root mean square. Remember, is V naught over root 2. So it means the peak value in the primary will be root 2 times 9. So this will be 9 times root of 2 to get the peak value in the primary. So it means now the value of V we want here will be equal to 9 times root of 2 times 8100 divided by 300. I press my calculator. Root 2 times 9 times 8100 divided by 300. So this is giving me 343, which is approximately 340 volts to two significant figures. Okay. State Faraday's law of electromagnetic induction. The magnitude of the induced EMF in a coil. Induced EMF in a coil is directly proportional. It's directly proportional to the rate of change of magnetic flux linkage. So that is Faraday's law. The output of an ideal transformer is connected to a bridge rectifier as shown in the figure below. So we see the figure here. The output is connected is shown in the figure below. Note that whatever is given here is always root mean square. The input to the transformer is 240 and the maximum potential difference across the load, that is peak, that is V naught of the secondary, is 9.0 volts. On the figure, mark with the letter P the positive output from the rectifier. So let's try to move around. So if current enters from this side, this is conducting, this will not and this will not, so it enters from this side. It continues, it comes out from this side. If this becomes positive and this is negative, current again will enter from the same point. It will take this route and enter from this point. So it means up is positive, bottom is negative. So they said label this P. So this is P at the top. P is at the top. Calculate the ratio, number of turns in the primary coil over number of turns in the secondary coil. Note that they have given us root mean square values and again a peak value. So you must be uniform, either use peak values for both or root mean square values for both. So number of turns in the secondary over number of turns in the primary will be, I will use the peak values, will be now V peak for the secondary over V peak for the primary. So remember, for the secondary they have given us 9 volts. So this will be equal to 9.0 volts. But for the primary they gave us root mean square. And remember, V root mean square is equal to V naught over root 2. So V naught is root 2 times that. So this will be root 2 times the V root mean square, which is 240. So you now press your calculator to get this ratio. Oh, we want primary over secondary. Sorry. I have to change this. So this is number of turns of primary over number of turns of secondary. This is primary, secondary. So this is going to be, for primary we have seen it is going to be, since they gave us root mean square, the peak is going to be root of 2 times the root mean square, which is 240, divided by the peak of second, which is 9.0. Then I press my calculator. So the ratio they are looking for is approximately 38. These are 3 free marks. They are just free marks. As long as you know this, you just substitute, and the examiner may want to mark this, so it should be part of the working. The variation with time t of the potential difference V across the load resistor in B is shown in the figure here. A capacitor is now connected in parallel with the load resistor to produce some smoothing. Explain what is meant by smoothing. We have already said smoothing is the reduction in the variation of the output unidirectional voltage or current. So to be precise, you can simply say current does not go to what? Current or voltage does not fall to 0. That is smoothing. Current or voltage does not go to zero, does not fall to zero. Okay, on the figure, draw the variation with time t of the smoothed output potential. So this is, it was full wave, so this is full wave. So since it was full wave, I'll do a reference point where my peaks should fall to. So let's say it stops here. So I will draw fluctuation, the peaks falling to that part for, let me increase the thickness. So you draw starting from the peak. I don't know, my mind might not be very exact at the peak because of writing on a computer. So the charging process, you draw the curving parts. Just pass there the pencil so that it appears as if it is bold, So that is charging, the other one is discharging. So charging, discharging, charging, discharging. That is the smooth voltage. That is the output of the smooth voltage. So these should be ending at the same level. They should be ending at the same level. Okay, a bridge rectifier consists of four ideal diodes A, B, C, D connected as shown in the figure. An alternating supply is applied between the terminals X and Y. On the figure, label the positive connection to the load R. So we move around. If this is positive and this is negative, this one will conduct and it can't take this route, so it will just take that route. So it enters from the top. If this is positive and that is negative, let's say, okay, it continues for the first case. It takes, this one will conduct, A and C is conducting. For the second half cycle, we take this route. C will not conduct, B conducts, it continues, it enters from the top, it comes, D conducts. So for the first half cycle, it is A and C. For the second half cycle, it is B and D which conduct. It is all, in all cases, entering from the top. So we put a positive at the top. The positive is at the top. Okay. State which diodes are conducting when terminal Y of the supply is positive. So when it is positive, that is the second half cycle. We are saying when terminal Y is positive, it is actually diode B and D. It is diode B and D. The variation with time t of the potential difference V across the load is R. The load resistor R is shown here. Okay, so we have seen that the load has resistance 2700 ohms. So we see the peak value V naught is 4 volts from the graph. Use the figure to determine the mean power dissipated in the resistor. Average power, we use root mean square values. Average power, we use root mean square values. So average power is going to be equal to V squared over R, but we shall use root mean square values. And remember, root mean square values, V root mean square is equal to V naught over root 2. So this will be V naught over root 2, but is what? Squared divided by R. So we now substitute. V naught is 4 over root 2, and this is squared divided by R, which is 2700. When you press your calculator, 4 divided by root 2 and squared divided by 2700. So we are getting 2.963 times 10 power negative 3. So to two decimal places, I have 2.96 times 10 power negative 3. So that will be the mean, the average power. Okay. Use the figure, on the figure, draw a symbol for a capacitor connected so as to increase the mean power dissipated. That is, to increase the smoothing, the capacitor must be drawn in parallel. So I will put here capacitor in parallel with the load. So that is the capacitor. Draw a nice capacitor in parallel with the load. Okay. Then on figure 6.2, which is the graph, draw the variation with time t of the new potential difference across the resistor R. The new potential difference across the resistor R when we have added a what? A smoothing capacitor. So the fluctuations are going to reduce. The fluctuations are going to reduce. The period, of course, is not going to be changing, and when we look at this circuit here, let's check. So for the first half cycle, X is positive, A conducts, it takes that route from the top, and it comes to C and comes back to Y. When Y is positive, then it flows through B, it goes to the load, and it comes back to D and back to X. So the capacitor in B is now removed from the circuit. The diode A in the figure stopped functioning. Let's check. A is no longer functioning. A is no longer functioning. Diode A is no longer functioning. Okay. So if diode A is no longer functioning, then it means we shall be having a most likely half wave. Diode A stops functioning, so that now it has infinite resistance. So if A is not functioning, let's see. For the first half cycle, B conducts and D conducts. That is fine. Second half cycle, Y is positive, B conducts, but because this is positive, B is conducting and D is conducting. When X is positive, A does not conduct, D does not conduct. That is half wave. So it means if we put a capacitor there, we are actually smoothing half wave. So this is half wave rectification. So it is half wave rectification because diode A in the figure was stopped functioning. So the second half cycle there is no current. So we are now going to draw the variation with the time t of the new potential difference across. Note that is now half wave because diode A has stopped working. So let us assume maybe it fluctuates for the second half cycle. Since the capacitor is removed and the diode has stopped working, so we only have half wave rectification. So we shall only draw the half waves. So I will have just use a pencil for this one. I skip that one. Here I will draw a horizontal line because it is 0. I draw this one, then I draw a horizontal line, and I continue with that one. So for the half, it will be half wave because first of all, the capacitor has been removed. There is no smoothing. And second, the diode A has stopped working. So it is now, we only have voltage on half of the cycle. So we shall have such a graph. We shall have such a graph. Okay. The same period, same peak value, but half wave rectified. Okay, state length is low. State length is low. State length is low of electromagnetic induction. Remember, length was concentrating on the direction. So direction of the induced EMF is such as to cause effects that oppose the change producing it. The direction of the induced EMF is such as to cause effects that oppose the change producing it. A simple transformer with a soft iron core is illustrated here. Explain why the core is made of iron. You can't get tired of that question. I told you this unit is short. Most questions are a repetition. There are no new questions in this unit. So the purpose of iron, we know iron is to reduce flux, the magnetic flux, or to reduce flux loss. Not to reduce the magnetic flux, but to reduce the flux loss. Iron is to reduce flux loss. Iron reduces flux loss. In fact, it increases flux linkage. It increases flux linkage, or you could say iron can easily be magnetized and demagnetized. Iron can easily be magnetized and demagnetized. Why the core is laminated? This relates to eddy currents. So to reduce energy loss or power loss due to eddy currents or heating caused by eddy currents in the core. To reduce energy loss or power loss caused by eddy currents in the core. So that's why it is laminated. Next, an EMF is induced in the secondary coil of the transformer. Explain why the primary coil gives rise to this induced EMF. Why does the primary coil give rise to the induced EMF? An EMF is induced in the secondary coil of the transformer. Why does the primary coil give rise to the induced EMF? Of course, in the primary we have SC. So alternating current in the primary. SC in the primary gives rise to a changing flux in the core. Gives rise to changing flux in the core. Alternating current in the primary gives rise to changing flux in the core. Note that the core links with the secondary. The core links the flux. The core links flux. The core links flux with the secondary coil. And by Faraday's law, a changing flux Changing flux induces EMF in the secondary coil, or induces an EMF in the secondary coil. So that's why the current in the primary gives rise to an induced EMF. It is changing. It is alternating. Because it's alternating, it gives a changing flux in the core, which spreads to the secondary coil. It is being cut by the turns of the secondary coil. A changing flux around the secondary coil by Faraday's law will induce an EMF. Okay. The mean value of alternating current is 0. Explain why alternating current gives rise to a heating effect in a resistor. That is a very simple question. The heating effect is proportional to I squared, or depends on the square of current, and is always positive. The heating effect in a resistor is proportional to I squared. I squared is always positive. I squared is always positive. I squared is always positive, so there is a heating effect. Because I squared is always positive, there is power dissipated. In other words, alternatively, I moves in opposite directions in a resistor during half a cycle, and the heating effect is independent of the direction. So you could say I moves in opposite directions in a resistor during half cycles, I moves in opposite directions in a resistor during half cycles, but the heating effect is independent. Heating effect is independent of direction of current. Heating effect is independent of direction of current. That is also one. You could also look at I and V. The power dissipated is equal to I times V, and I and V are always in phase. The product is always positive. By reference to heating effect, what is meant by root mean square value of alternating current? The value of DC producing the same heating effect in a resistor as SC in a resistor is what we call the root mean square value. The value of direct current producing the same heating effect, or the same power. The same heating effect as the SC in a resistor is what we call the root mean square value of alternating current. It can be that value of alternating current which produces the same heating effect in a resistor as direct current. That's what we call the root mean square value of alternating current. Okay. A simple ion powered transformer is illustrated here, as we can see. As a primary coil, I think it is a step up in the secondary coil. State Faraday's law of electromagnetic induction. Of course, we know that the magnitude of the induced EMF in a coil is directly proportional to the rate of change of magnetic flux linkage. Use Faraday's law to explain why the current in the primary coil is not in phase. We have explained this. We have said the magnetic flux in the core, or the magnetic flux in the core, is in phase and proportional to the current in the primary, or the EMF in the primary. And this links with the secondary, and by Faraday's law, an EMF is going to be induced in the secondary because the secondary coil cuts the magnetic flux. However, the induced EMF depends on the rate of change of magnetic flux, so they cannot be in phase. So we said the magnetic flux is in phase. The magnetic flux is in phase. The magnetic flux is in phase and proportional to the EMF or the current in the primary coil. And, but I will use but. The magnetic flux is in phase and proportional to the EMF or current in the primary coil, but the EMF induced across the secondary is proportional to the rate of change of flux. That is according to Faraday's law. The magnetic flux is in phase and proportional to the EMF or the current in the primary coil, but the EMF induced across the secondary is proportional to the rate of change of flux according to Faraday's law. So the EMF, because when we said when the magnetic flux is maximum, the rate of change is zero. And when the flux is zero, the rate of change is maximum. So the EMF of the supply cannot be in phase. With the PD across the secondary, or the EMF of the supply or of the primary. The EMF of the primary, let me just say the EMF, because here they said why the current in the primary coil. So I'll say the EMF of the primary cannot be in phase with the EMF across the secondary coil. So that is as simple as that. By Faraday's law, an EMF is induced in the secondary because it cuts, because there is a change of flux, or there is a because of the rate of change of flux, and the rate of change of flux is not in phase with the magnetic flux. So the magnetic flux is in phase and proportional to the EMF in the primary coil, but the EMF induced across the secondary is proportional to the rate of change of flux according to Faraday's law. So the EMF of the primary cannot be in phase with the EMF across the secondary because the magnetic flux is not in phase with the rate of change. I can add because flux is not in phase with rate of change. Flux linkage is not in rate. Magnetic flux is not in phase with the rate of change of magnetic flux linkage. Okay. A student is using a power supply that produces a sinusoidal output. The meters on the supply show that the output V has a root mean square value of 14 volts with a frequency 750 Hz. The variation with time t of the output is given by this, may be represented by that expression. Determine the value of V naught. Determine the value of V naught. They have given us the root mean square as that. So we know that V naught is equal to root 2 times V root mean square. So this would be 14 times root of 2. And 14 times root of 2, I think that is 19.8 volts. Then omega, we know that omega is equal to 2 pi f. So this would be 2 pi times the frequency, which is 2 pi f, 2 pi times the frequency, which is 750, and that is 2 pi times 750. So this is 4712.38, which is approximately 4,700 radians per second to two significant figures. 4,700 radians to two significant figures. This is 4712.39, not 38. A capacitor with a large capacitance is connected across the terminals of the supply. Suggest and explain why this may lead to a large current from the supply. A capacitor with a large capacitance is connected across the terminals of the supply. Why would this lead to a large current from the supply? So a large amount of charge is going to be required to charge this capacitor. A large amount of charge is going to be required to charge this capacitor. And remember, current is the rate of flow of charge, that is Q over T. So it means if there is a large amount of charge required to charge the capacitor, then the capacitor would charge and again discharge rapidly, but in a very short period of time, meaning Q over T will be larger. So it means the current will be larger. So a large amount of charge, is required to charge the capacitor. Is required to charge the capacitor. The capacitor would charge and discharge rapidly. The capacitor charges. The capacitor would charge. The capacitor would charge and discharge very rapidly. When I say very rapidly, it means in a very short time. a very short time. So it will discharge in a very short time. Because it requires a large value of Q, since I is equal to Q over T. A large capacitor means it requires a large amount of charge to charge it. It requires a large amount of charge for the capacitor to be charged, and this would the capacitor would still discharge rapidly when given a chance to do so. So it means it has a large charge and is discharging it in a very short time. If current is Q over T, so it means there will be a large current. So large current. As simple as that. In many distribution systems for electrical energy, the energy is transmitted using current at high voltages. This question will appear many times. Suggest and explain an advantage, one in each case, for the use of alternating. Why alternating? We said if it is alternating, the output voltage can be changed efficiently to suit different consumers. So output voltage can be changed, of course, using transformers, can be changed. Output voltage can be changed efficiently. Using transformers. Of course, this is to suit different consumers. So using transformers, we can step up or step down the voltage if it is alternating, so that we can meet our consumer demands. That is an advantage of using alternating. It can readily and easily and efficiently be stepped up or stepped down depending on the consumer demands. That is the advantage of using alternating. High voltage, we saw that for the same power transmission, high voltage means smaller current, means a small current flowing through the cables. This means a small current flowing through the cables. A small current is flowing through the cables, and if there's a small current flowing, there's less heating. Thus, less heating. Thus, less heating in cables, or you talk about less power loss. Also, by the way, if we use high voltages and a small current is flowing, then that means thinner cables are possible. So you would say thinner cables are possible. Of course, thinner cables are cheap. Thinner cables are possible because thinner cables are cheap. Why is it possible to use thinner cables? Because a small current will be flowing. So thinner cables are possible and thinner cables will be cheap. Okay, the output potential PD of the output potential difference of an alternating power supply is represented by this equation here. Compare with V equals to V naught sine omega t. Okay, V is the PD in volts, T is in seconds. Determine the root mean square PD of the power supply. Root mean square PD of the power supply. So we know that V root mean square is equal to V naught over root of 2, which is going to be equal to 320 divided by root 2. And I press my calculator here. So this gives us 230 volts. Determine the period T of the output. So we have been given omega as 100 pi, and omega is equal to 2 pi over T. So it means T is going to be equal to 2 over 100 because pi cancels, and this is 0.020. So this is 0.020 seconds. The power supply is connected to a resistor R and a diode in the circuit as shown here. State the name of the type of rectification produced by the diode. This is automatically half wave. Half because it's a single diode which allows only one half of the current, one half of the cycle to have a voltage. So this is going to be half wave. That is half wave rectification. On the figure, sketch the variation with time t of the PDVR across R from t equals to 0 to t equals to 40 milliseconds. T equals to 0 to t equals 40 milliseconds. Note that the period is 0.02. We have calculated it above seconds. This is the same as 20 milliseconds. That is one cycle. So it means in 40 milliseconds, we shall have two cycles. Okay. Note that it is half wave rectified. So here we shall have one cycle and a second cycle. Remember, one half is always lost for half wave rectification. So between 10, I'll just do a horizontal line. That half is absent. Between 30 and 40, I'll do a horizontal line. Then what was the peak voltage? The peak voltage was 230. So I'll look for the peak voltage was 320. So I'll look for 320 from the graph. So here it is 100 divided by 5. That is, each of these is 20. So I'm looking for 320. That will be one small square. So the peak will go 1, 2, 3, 4, 1, 2, 3, 4, 5. The peak will be here. The other part will be 0. So 1, 2, 3, 4, 5. The other part will be 0. Let me try to rectify this. Okay, so that will be the graph half wave rectified. Note that the period was 0.02 seconds, which is 20 milliseconds. And yet they gave us 40 milliseconds. Those are two cycles. This is sinusoidal, but we have eliminated the negative part of the cycles. We have only the positive part, peaking at 320 because they told us V naught was 320 from the equation. The peaks should be at 320 volts, and we shall not have the second half cycles. We shall not have the second half cycles in both cases. So that is, alternatively, we would draw these peaks only on the negative part, not on the positive, because we cannot have both at the same time. Okay. On figure 10.11.1, which is the diagram, draw a symbol for a component that may be connected to produce smoothing of VR. So we use a capacitor, and it is going to be connected in parallel with the load. So that is for smoothing, as simple as that. Okay. State what is meant by capacitance of a parallel plate capacitor. We shall see this in more details under the unit capacitance, which is the next. So capacitance is the ratio of the potential difference, because capacitance is Q over V, charge on one capacitor plate, because total charge between the two capacitor plates is 0. So it will be the ratio of the charge on one capacitor plate, on one plate, to the PD, to the potential difference, between the two plates. Between the plates. Because if this is the capacitor, these are the capacitor plates, the charge on each plate is one is positive, one is negative. The capacitor is fully charged when the PD across the plates is the same as the voltage supply. So it's the ratio of the charge on one of the plates to the potential difference between the plates. Okay. A capacitor of capacitance C is now connected into the circuit as shown here. Okay. We see the circuit. So the switch can be turned, we can turn this to A, we can also turn it to B depending on what we need. When the two-way switch is in position A, the capacitor must be charging. When the two-way switch is in position A, the capacitor is charged so that potential difference across it is V. The switch moves to position B and the capacitor fully discharges through the sensitive meter. The switch moves repeatedly between A and B so that the capacitor charges and then discharges with the frequency F. Show that the average current I in the ammeter is given by that expression I is FCV. So we know that current is equal to charge over T. And we know that the charge Q is given by C times V. And we also know that the time is going to be 1 over the frequency, the time of discharge. The time is going to be 1 over the frequency, which is like the period. So we now combine these three expressions. So it means I is equal to CV over T. I is CV over T. And 1 over T is F, which means that I is going to be CV times F. Because 1 over T will be F. 1 over T will be F. Since T is 1 over F, 1 over T will be F. So 1 over T is going to be F. So this gives us that. For a potential difference V of 150 volts and a frequency of 60 Hz, the average current in the ammeter is 4.8. Calculate the capacitance in picofarads. So we just substitute in the equation I is equal to FCV. So we want to find the capacitance C. So C is going to be the current, which is 4.8 times 10 power negative 6 divided by F, which is 60, times V, which is 150. Press my calculator. So this is actually 5.33 times 10 power negative 10. That is negative 10. It is in farads. So I have to change this to pico by dividing by 10 power negative 12 to change it to picofarads. And this is giving me 533. So this is 533 in picofarads. I will just write 530 in picofarads. The second capacitor, having the same capacitance as this capacitor in B, is connected to the circuit. The two capacitors are connected in series. So having capacitors in series reduces the capacitance. They have the same capacitance and they are connected in series. State and explain the new reading on the ammeter. When it was one capacitor, the reading of the ammeter was 4.8 microamperes. When they are connected in series, we are seeing that from the equation I is equal to F C times V, I is directly proportional to C. When they are connected in series, total capacitance reduces by a half. So since the capacitance halves, then the current also should halve. So this is going to be 2.4 microamperes. Reason: total capacitance is halved. Total capacitance is halved. When we connect two capacitors in series, total capacitance reduces. Now these are identical, so total capacitance is halved. So it means the discharge, it means if the total capacitance is halved and yet I is directly proportional to the current, it means the current should also be halved. So total capacitance is halved and current, or you can say, if you want to give details, the charge for each cycle, the charge for each cycle, the charge for each cycle, or for discharge, the charge for each discharge is halved, And since F and V are constant, they are not changing. And since F and V are constant and they are not changing, it means the current is directly proportional to capacitance. The current is going to be directly proportional to capacitance. The charge for each cycle is halved because total capacitance is halved. Since F and V are not changing, then the current is proportional to the capacitance. So when capacitance is halved, it means the current should also be halved. The output of the supply is given like as this, compare with the V equals to V naught sine omega t. V is the potential difference in volts and T is the time in seconds. Determine for the output of the supply the root mean square value. So we know V root mean square is equal to V naught over the root of 2. V naught is 9.0 divided by root of 2. Press the calculator. So this is over root 2. So when I press my calculator, I'm getting 6.4 volts. Okay, next, find the period. Find the period. From the equation, they gave us omega as 20. And we know that omega is 2 pi over t. Omega is 2 pi over t, which is 20. So it means the period is going to be 2 pi divided by 20, which is, from my calculator, the period is 0.31. That is the period. Okay. The variation with time t of the output potential difference V from the two power supplies are shown here. The graphs are drawn to the same scale. They are drawn to the same scale. State and explain whether the same power would be dissipated in a 1.0 ohm resistor connected to each power supply. Of course, we need to look for the root mean square values, because the root mean square values are the ones which will tell us whether the same power will be dissipated. And when you look at the shapes of the graphs, you notice that the root mean square values will not be the same. The root mean square values will not be the same. And if the root mean square values will not be the same, then it means they will not dissipate the same power. Somebody may be wondering, how do you see that the root mean square values are not the same? So you notice that this, for the square wave, this remains constant for the long period of time. The peak remains constant for a long period of time, yet this fluctuates and it varies. And this just switches from maximum to another maximum. And then from one maximum to another maximum. That means the root mean square values the root mean square voltages are not going to be the same. They are actually different. This is all sinusoidal, the other one is square wave. So the root mean square values cannot be the same. Since the root mean square values, even though the peak values are the same, the root mean square values are different, then it means we cannot have the same power. So we are saying the root mean square voltages are different. The root mean square voltages are different. You could even see that they are different actually. Reason: for the second wave, there is no fluctuation. It just jumps from one maximum to another maximum. So the root mean square value does not follow. The voltage here does not follow a sinusoidal. Does not follow a sinusoidal variation as we see in this one here. So the root mean square values are not the same. And if they are not the same, then it means the power will not be the same. So the power would not be the same. The power would not be the same. Okay. The power supply in A is connected to a transformer. The input power to the transformer is 80 watts. The secondary coil is connected to a resistor. The root mean square voltage across the resistor is 120 volts, and the root mean square current in the secondary is 0.64 amperes. Calculate the efficiency of the transformer. So the average power, we know that average power is equal to I root mean square times V root mean square. So you can find because the power input in the transformer is this, let's look at the power output. So the power output, the average power output, we'll consider root mean square values. So we have one for voltage, we have 120, and for current in the second, we have 0.64. When I press my calculator here, this is 76.8 watts. That is the output power. But the input power is 80, so the efficiency remember is power output over power input times 100 if we want it as a percentage. So this is going to be 76.8 over 80 times 100. So when we talk about input power, we are looking at average. When we talk about input EMF in a transformer, we are looking at the root mean square values. So this is going to be approximately 90, that is 90 what? Plus 96%. So the answer here is going to be 96%. State one reason why the transformer is not 100% efficient. We stated the sources of energy loss in the transformer. There are so many. One, you can talk about loss of flux linkage. Two, you can talk about hysteresis losses in the core. Hysteresis losses in the core. Loss of energy due to continuous magnetization and demagnetization. You can talk about heat losses due to resistance of coils. Heat losses due to resistance of the coils. You can also talk about, of course, heat losses due to continuous magnetization and demagnetization, that is hysteresis. You can also talk about heat losses due to eddy currents in the core. Heat losses due to eddy currents in the core. Heat losses due to eddy currents in the core. Okay, those are some of the reasons as to why the transformer is not 100% efficient. Next, a bridge rectifier using four ideal diodes is shown here. The sinusoidal alternating EMF applied between points A and B has a root mean square value of 7.0 volts. On the figure, circle the diodes that conduct when point B is positive. B is positive, of course it means A is negative. When B is positive, current is flowing in this direction. This one cannot conduct, the other one can conduct. So we draw a circle around this one. So this diode cannot conduct because it is the other way around. So current will take this other route, and it will come back to this one. I'm saying when this one conducts, current is like this. It can't take this route because the diode is the other way around. So it will take the other route. So it will follow this route. It cannot come back again to high potential. So it will come back to this until it comes to lower potential. So it means it is that one and this one. They say circle the diodes. So it is this one, it is this diode here and the other one. Calculate the maximum potential difference Vmax across R. The maximum potential difference Vmax, that is V peak, V naught is equal to root 2 times V root mean square. So that is root 2 times V root mean square, that is 7.0. So the maximum is root 2 times that. So this is 9.9. 9.9 volts, that is the maximum. Okay. The capacitor is connected into the circuit to produce smoothing of the potential difference across R. The variation with the time t of the potential difference V across R is shown here. So you see the magnitude of the ripple or the fluctuation. On the figure, draw the symbol for a capacitor connected so as to produce smoothing. So a capacitor, we must draw a capacitor so as to produce smoothing on this figure 10.1. So look at which diodes, because the capacitor must be drawn parallel with the load. So we shall draw a capacitor here across the load to produce smoothing. Okay. Then state the effect, if any, on the magnitude of the ripple on V when separately. A capacitor of large capacitance is used. Of course, using a large capacitor increases smoothness, so the ripple decreases. The ripple decreases. The size of this ripple becomes smaller. It may stop somewhere there if we use a larger capacitor. Then the resistance R has a smaller resistance. They said separately. When we have a smaller resistance, the product R times C becomes smaller for the same capacitance. Therefore, the ripples increase. So here, the ripple increases. Last equation is number 10. A bridge rectifier contains 4 diodes. The output of the rectifier is connected to a resistor R as shown here. The variation with time t of the input EMF E of the rectifier is given by that expression. We can now compare this with E is equal to E naught cos omega t. So it is a cosine curve. The variation with the time t of the potential difference V across R is shown in the figure. It is a cosine curve. Determine the maximum potential Vmax across R. When you compare, you see that E naught is 15, so Vmax is going to be 15 volts. Then, what is this? Sorry. Then, the time interval to two significant figures between time t1, time t2. We want time interval. So, from here up here, that is one cycle. That is a second cycle. So that is twice the period. The time between t1 and t2 is twice the period. So we need to find the period. Note that omega is 210. Omega is 210. So we know that omega, what is wrong with this? Omega is 2 pi over t. Omega is 2 pi over t. And t therefore is going, and this is by the way equals 210 as from the equation given, it is 210. So t is going to be 2 pi divided by 210. And remember, we have seen the time between t1 to t2 is twice the period. So it means we shall multiply this by 2. So this will be twice times 2 pi over 210. So press my calculator. That is 2 pi times 2 divided by 210. So this is 0.0598. 0.0598. So the answer, they said to two significant figures. So to two significant figures, state the time interval for two significant figures between t1 and time t2. So this is going to be 0.060 to two significant figures. 0.06 0.060 to two significant figures, and this will be our final answer. I think that is the end of alternating current. It has been short. It is just one lesson. I hope you have enjoyed this. And on this video, I have attached a link on past paper questions paper 2 because I want to start recording them at the end of this month, of the month of November. So you can download use the link, ask for permission to download to use the link and download or access the document or paper 2. Print, have it ready so that when we start recording, you'll be following. Thank you for watching this video up to the end. The next video will be of capacitance, and I hope you enjoy it. Have a nice weekend if it is a weekend, wherever you are, and enjoy the day. Bye bye.